thank you very much for the kind introduction, and here it is. I can get this working, the slides. Okay, I would like to thank the organizers for the kind invitation. And today I'll be talking about quantum optics using artificial atoms in superconducting circuits on a chip. I will start first with a pedagogical introduction of the basics, and then afterwards introduce some recent results published the past year. So therefore, for the students in the audience and postdocs, we have a website. It's easy to remember. There is written right there on the top left corner, has many pedagogical reviews on quantum information, photonics, and other related topics. The PDF files are all available there for free. There is reviews on quantum information. There are 22 reviews, including popular ones in Physics Today, Science, Nature, and Nature Physics, etc., and many different reviews on physics. And there are also on different websites. If you click here, there will be review papers for other topics, mostly photonics and other subjects, quantum thermodynamics. And then, so therefore, let's start here with an approximate correspondence between quantum optics, atomic physics, and quantum superconducting circuits. When people study quantum optics and AMO, atomic physics, then you need to replace the atoms and ions by Josephson junctions, which we'll see in a moment is a sandwich between a superconductor, an insulator, and another superconductor. Lasers by generators, optical fibers and beams by transmission lines and wires, mirrors by capacitors, beam splitters by couplers, and photodetectors by amplifiers. So this is an approximate correspondence. And then so if you have a simple circuit like this, you make it very small, then this is a harmonic oscillator. Then there are quantized energy levels that are equally spaced. These are difficult to control because the energy spacing between 0, 1, 1, and 2, 2, 3, they're all the same. So you want to have different energy spacings. This is non-negotiable. Otherwise, you cannot target the transitions between level N and level M. This is done via nonlinear inductance. So therefore, nonlinear inductance essentially is this one here called Josephson junction, named after Brian Josephson, who was proposed for the first time. A typical one is here, aluminum, aluminum oxide, aluminum, and as you can see here, the sandwich is very small, like a couple nanometers or less. So therefore, replacing the LC circuit by this is all it takes. This is the key, the important step in the magic. And this gives you energy levels which are not like this, but energy like this. And then you can excite this with microwaves, either to 1 or to 2 or to 3, and you can study tunneling here. And this is the experiment done by Clark, Deborah Martinez, that led into the Nobel Prize a few months ago, like last December. So this is a key step. You go from a linear oscillator to a nonlinear one, and then you can actually target with microwaves different energy levels, and then see these nice effects. I'll be talking more about the Nobel Prize results in a moment. So here,
could you press on the hide button? Sorry, because otherwise partial text we can see in the bottom of middle. Enable with hide.
I see. Well, hide.
Not hide.
Okay, good. Okay, now, so sorry. So this is called a phase qubit. It's tunable with an applied current. So therefore, so it's replacing the linear oscillator with nonlinear one. These are the key steps, and the motivation is clear because you want to have control, and this relates to the Nobel Prize of last year. Okay, this is the same system studied by Martinez, Deborah, and Clark. So again, you replace the atom by Josephson junction, light sources by current and voltages, and microwaves detected by voltmeters and ammeters. So what you're doing is you're taking an atom, a large atom made of a condensed matter system, like this Josephson junction, and you're applying voltmeters and ammeters. So you're wiring up atoms. So you're putting a large atom on a circuit, on a chip. And this is what IBM has been doing, Google, and many companies. You put atoms on the chip, but you need to control them. Of course, they operate at different temperatures. Still being at 300 Kelvin will be about 30 millikelvin. So there is a different orders of magnitude there. There is an electrodynamic environment here, and this is a cavity. The cavity is needed because the atom and the light can interact well only inside the cavity because the coupling is very, very weak. So the light is bouncing on the cavity back and forth many times to enhance the coupling. So here is a weak atom field coupling. In this case, is strong. This is important. The revolution between these results obtained by, this is the Nobel Prize by Serge Haroche some time ago, is about these fantastic results that you can find when you do light matter coupling, but the coupling is weak. Once you go to here, it's a revolution. The second quantum revolution was pushed by this strong coupling, and strong means 5 orders of magnitude to 6 orders of magnitude stronger. So it's a major, significant difference. And they both have photon loss and the dissipation and decoherence, and these are the usual things. Okay, so the light matter coupling is extremely weak for atoms in a cavity, and also this is a Haroche Nobel Prize system. Also, Yoshimoto and others have been working on this for a while. 5 or more orders of magnitude stronger using superconducting circuits with Johnson junctions. That's the key idea. Now you can use this not only for quantum computing. This is misleading. This is very limited. You can use it to study resonators, it's like an organ pipe or like a guitar at the quantum level. And this can be used to do a quantum bus to communicate between different qubits. You can use it to have exactly 2 different qubits talking to each other. So resonator is like this pipeline where they're actually talking to each other, with microwave lines. You can have tunable resonators that act like a trombone. So you change the frequency of the organ pipe, so it acts more like a trombone, and then this is useful for other kind of applications. You can look at photonics, quantum limited amplifiers, masers, bifurcation amplifiers, parametric amplifiers. So there is a lot of things you can do with this, and also like molecules. Once you join them together, you can do like, instead of 2 artificial atoms, you can study different artificial molecules. Of course, if you keep adding them together, these molecules, you could have different devices that will lead to, for instance, quantum computing, either analog ones, which are the ones mostly people are using, and digital ones, which are still people working on for future use. Okay, so now we go into this. So the first few slides of this talk will be how superconducting circuits operate to study atomic and optical physics, so more the basics. And then at the end, one growing research direction involving further increasing the light matter coupling. So therefore it's pushing this direction even further. So here you have this red giant atom here interacting with this one blue via these waveguides. These coplanar waveguides are confined in the electromagnetic field, so the photons here interact with this atom here on this, and then it begins to move through this path here, interact with this atom here, and then talks to this atom here again over here, and then back to this atom back here. So there are different ways people are exploring now to make them to interact, and this can be done theoretically, can be done experimentally, and it's given rise to exciting results. These large atoms can be used to actually produce sound, which are detected by a microphone here. This is the first giant atom done at Chalmers about over a decade ago, Gustafson et al. But also you can generate sound with this capacitor. This is a whole bunch of capacitors called interdisciplinary capacitors, where you produce quantum sound via surface acoustic waves, and you can actually excite this qubit not only with microwaves but also with sound. So you can go from the ground state to excited state either via light, photons, microwave, or via sound. So therefore, this superconducting qubit can also listen to sound, not only see in the microwave, but also to listen. So this is a remarkable new. And then at the end, we'll be talking about nonlinear optics with one or few photons, because nonlinear effects in optics are weak and require many photons. And then these effects can be observed with, the question we're asking is, what can you see when you have very few photons? And then nonlinear optics is used for telecommunication industry and many other applications involving a three-way mixing, degenerate three-way mixing, a down conversion, up conversion, when you have two frequencies going up, one frequency going down. You sometimes want to up convert the signals, lower frequency to study spontaneous Raman scattering, stimulated Raman scattering, and then essentially either to add them up or take differences. So there are different ways to operate this, and they're very, very useful. This corresponds to general four-way mixing and general three-way mixing. These are exciting areas of nonlinear quantum optics being studied now with these superconducting qubits. An example here was by the experiment by Jian Chen-Yao in Hangzhou in China with mostly collaboration with collaborators in Italy, my group, and most of the effort was done in Hangzhou. Strong coupling between a single photon and a two-photon Fock state. This is essentially like a photon state. And then it was published 2025 in the fall. I'll be talking about this afterwards. Now, the main physics is summarized in the next slide. This is haiku. It's a 3 lines, popular Japanese poem, which is popular in Japan here. The superconducting circuits can behave like atoms, making transition between discrete energy levels, and these can test quantum mechanics at the microscopic scales and be used to conduct atomic physics and quantum optics experiments on a silicon chip. So it's more than just quantum computing. It's more general. This is something that is important to keep in mind. And this is taken from the abstract of our Physics Today review. So when I see a 5 or 6 page review, you go to our website. It has been translated into many different languages. The basics is there. There's another review in Nature, which is very, very simple to read, and also longer ones in Physics Reports, and there is one in Physics. So now this relates to the Nobel Prize last December. So this is important to be able to link them. So I'm going to, so this is for the discovery of macroscopic quantum mechanical tunneling energy quantization in electric circuit. This is Clark, Michel de Martinez. And this is a photo I took there. So they, when it was announced, October this, we were invited to participate in the entire Nobel Week. And let's quickly see some photos, because people keep asking me all the time, hey, can you show us what is going on at the Nobel Week? So I'll do a quick overview here, so because that's what people keep asking me. So therefore, they're there. He was the advisor at the time, the postdoc at the time, and the graduate student at the time. And then that was like in the early to mid 1980s. That was a long time ago. So therefore, Monday morning, there is the welcome to the Nobel lecture. So therefore, it's a lecture explaining the past, the discovery, and what came afterwards. So at that point, they come to the stage, and then each one of them gives presentations here. They were very nice presentations. And afterwards came the one in chemistry, and then the one in medicine, and the one in economics. And so therefore, Monday night, there is a concert. This is the Nobel Prize concert here. This is a huge organ pipe. And then this is the physics section of the first balcony right next to the royal family. And then the concert was really amazing. And then there was a dinner afterwards. And then I gave them a replica. This is not the Nobel medal. This is a replica. This is Deborah and Clark. And also I gave one to Martini. That was the night before. The real one is larger and is coated with real gold. This one is not. So, and then we went to the ceremony. You get to be invited to get there. And then the ceremony is here. So at the concert, the musicians are on top here. These are former Nobel Prize winners and some dignitaries there. I think Angela Merkel might have been there also. And here they are members of the selection committee for different. And then here, these blue and yellow chairs will be taken over by the royal family, and the red ones by the winners. The 3 ones in physics, then chemistry, medicine, and economics. And then these were the essentially mandatory dresses, like a dress like a penguin, we'll show in a moment. It was a very, very nice palace here. And then, so therefore, here is the royal family here. And then the ceremony start, and there is a speech. Okay, this is the royal family here, and King Gustav, other members of the family. And then this is Göran Johansson, who is member of the selection committee, giving the speech for the physics Nobel Prize. And then this is John Martinez getting the award. That was on Wednesday, December 10th. And then this is exactly the member of the Nobel selection committee giving the speech. And then we happen to have written many papers together in the past in physical letters, Nature, and some of them cited very, very highly. So he's a great physicist. Here in the back, there is another King Gustav, but this one is like from many centuries ago. And then here, there is a ex-Google people, ex-Google right now with Martinez, ex-Google Hewlett Packard, and this the director of the Quantum Computing Center here in RIKEN, who did very important work in the 1990s and afterwards this century on quantum computing here. And this is with my wife in the ceremony area here. Is before the banquet, so the king and the royal family and the big shots are here with it, and then there are a whole bunch of guests sitting all over. There's a concert here on quantum entanglement. I didn't see the relation on entanglement, but it was a great, great concert. And then, so here it is. My daughter put this on here. So the person without hair there, that's myself. And then here's the physics people, and then the chemistry, and then the medicine, and the economics, and then there's also literature. And then those are the concert, and then afterwards there is this like something like 100 waiters distributing food all over here. This is the banquet after the ceremony. This is Martinez here, Clark, the king and the queen, and the guy with no hair is there. These are the 2 sons of John Martinez, my wife, and then some other people were with the physics group here. These are table. I took this photo here, and then these are the physics people and the chemistry, so on. And then further back, medicine and economics. One of the sons of John Martinez here, and then so this was on Swedish television. Is Martinez, Clark, the son of Martinez, and myself here. So therefore, you got to see superconducting circuits have been in the news lately. So, and then let's explain these, the important significance of this. If you're interested, it's a 9-page long review in Nature by a former postdoc of mine and myself here on atomic physics and quantum optics using superconducting circuits. And then we also have a 100-page review you want to see, and also a 9-page review. And then if you want to see a cartoon of it, some people say they want to have only 1 slide summary. This is it. The cartoon summary, also using 3 lines, is coming now. This is from here. We have here atoms, semiconductors, superconductors for electric field equal to 0. The blue curves are the potential energy, the red line, the discrete energy levels. We put an electric field, of course, this is tilted. And this is the kind of system called phase qubit, and which is essentially what Martinez, the Clark studied in the mid-80s. So this is a relation between this atom and the Nobel Prize that was given a few months ago. So essentially, that's the key idea. You want to have this non-equally spaced, so you don't want to have a linear inductor, so you put adjustment junction. And then that's it. That's the main idea. Now, let's focus on this one here and not on atom semiconductors. And this is one called charge qubit of different type. You can stack them in groups like this for chips. So in this case, there is here a box with electrons. This capacitor here is pushing electrons in and out of the golden box. You can have from n to n plus 1 electron pairs. And this corresponds to your 0, 1, where your grounds at the side state. So you have here a control, which is the electric knob and magnetic knob. So you have 2 knobs. This knob would produce Larmor frequency precession along the z-axis because it's multiplying. Larmor frequency along the x-axis because it multiplies sigma x. Sigma x, the Pauli matrix control the kinetic energy. You go left, right, right, left. This is the off diagonal. This one here is the on-site Coulomb repulsion, which is controlled by the capacitor. So this controls the rotation, the Larmor frequency around the z-axis. So you have two knobs to control the motion here, because this field controls the strength of this barrier. So these are the tunable barriers. These are the Josephson junctions. So you control them with the magnetic field, and this one here with the electric field. So by doing this electric knob, magnetic knob, you control you're opening and closing these gates here. You're pushing the electrons in and out. But this corresponds to rotating the state of the system on a block sphere. You do that by changing the electric knob and the magnetic knob. So this is the key idea. If this slide is understood, you understand the basics of essentially, because this transmon qubit essentially is a charge qubit. Like this one here. You need to put a capacitively shunted version of this. So the goal is to control the artificial two-level system in a solid-state device. You replace this system by this one here, and you try to control it and generate these systems on a block sphere. So this is the block sphere, so you have this 0 and 1, but it's multiplying by this theta, so you can actually control this yellow vector back and forth on the sphere. So this is very important. So you can do rotations along the z-axis, Larmor frequency there, along the x-axis, when you change the magnetic field and when you change the electric field. This in NMR language, there is a free evolution. You can have pi over 2 pulses, pi pulses, they're all taken from NMR. And then this is done with sigma x, rotation on x, and this one rotation with sigma z. So now many people confuse Larmor frequency with cyclotron frequency, especially some students. The first person to consider this the difference was William Shakespeare. This is not well known. Indeed, Hamlet, the king of Denmark, the prince of Denmark, he was obsessed with this issue. He kept asking over and over, to E or not to E? That is the question. So therefore, the genius of Shakespeare was to focus on the magnetic field, and you put the magnetic field before the electrical charge E, and when you flip these two here, when you flip the order, then you get the following. You get to B or not to B. That is the question. And this resolves the issue that was tormenting Hamlet between the cyclotron frequency and the Larmor frequency. As you can see here, Shakespeare was very pleased. So now we understand the difference between both of them. In one case, is precession along the axis of rotation of a magnetic moment when you apply a magnetic field, and the other case is the rotation of an electrical charge on a magnetic field. Then you have this Josephson energy multiplying sigma x and the charging energy sigma z. So these are Larmor frequency rotations along the z-axis and Larmor frequency rotation on the x-axis, because the Pauli matrices control these rotations. Okay, so you can do different pulses, and then you can control rotation along the x-axis, along the z-axis, and so on. So by doing this, you can control the state of the system. Now, there are many analogies between natural atoms. These are discrete energy levels, coherent quantum oscillation between those levels. The natural atoms are controlled using visible light or microwave photons that excite electrons from one state to the other one. The artificial atoms in the circuit are driven by currents, voltages, and microwave photons. So there are different ways to control them. There are more knobs: electrical knob, electric knob, and the photons, which are right here. And then, of course, they couple to the system very differently. The coupling is weak for atoms and strong for circuits. The energy scales are different. And the artificial atoms can be lithographically designed to have characteristics you want. You want to have a larger dipole moment, you want to have different frequencies. So you have control. You're creating atoms in the lab. And this is important. This opens a new direction on quantum nanoelectronics that goes way beyond quantum computing. Again, this is a charge qubit here, box of electrons, push electrons in and out, tunable barrier. And now, but you can have also flux qubits, phase qubits, but it doesn't matter. They all have, when you diagonalize, you have here many energy levels. You can magnify the green box and you get 2 ones for the qubit, but typically people consider 3. or fourth, because you can have this is auxiliary level. You can do more things, especially for quantum optic simulations. And you can have atoms which are lambda type because this looks like a lambda, V type because this looks like a V, ladder like or like chi because it looks like a chi, delta type atom. These are not allowed for normal atoms due to the electric dipole selection rule. Delta L equals plus minus 1. You can go from even to odd to even, but you cannot go even to even. That would be odd. You can have up conversion, 2 photons generating 1, down conversion. This one here, exactly that. So this one generating two frequencies, omega 1, omega 2. So you can do frequency conversions. You can do electromagnetically induced transparency where the atom is opaque. You shine a laser, is absorbed, is dark. But then you can make it the transparent electromagnetically induced transparency. You put another laser. This is needed. It needs a lambda sequence. There is the blue atom, the blue laser creates transition, and then you create the transparency with the orange laser. You can do state population inversion for lasing. You can essentially go the system in this direction and here, and eventually allow this to go down when you want it. You can do cooling a 3-level atom nearby 2-level system. So essentially you're pumping energy from the atom to a 2-level system. You can actually transfer information between different qubits via cavity. So the cavity allows like a bus, like a data bus. It would be good for communication or quantum computing. So in summary, we have different kind of atoms which have discrete energy levels. This allows you to control the kind of transition they have. It allows you to do nonlinear optics, allows you to do electromagnetic transparency, state population inversion for lasing, cooling, transference. It allows you to do many things because you have control. There are different knobs you can play. So this is the overview, and this is all in our review in Nature. These are plots from there. It's like 11 pages, but I mean, they're almost no equations. This is like very, very simple. Now we have long reviews, which are like 100 pages long or something like this, where we're looking at the more recent versions, which are essentially the same ones I showed before, but slightly modified. This Cooper per box with a squid, controlling transmon. But the question is, what do you want? You want to have tunable Josephson energy? You want to have charge noise reduction? Or you want to do tunable coupling? You want to do improved connectivity? You want to do flux noise reduction or charge noise reduction? So therefore, depending on your goals, there are different circuits. It's not that there are which one is better or worse. There are different goals. There are different targets. So people design different atoms to address different needs or different preferences, depending on what you're looking for. So these are explained in great detail in our pedagogical reviews there. So this is a chart of different extensions and refinements of the 3 basic ones which I showed before. And this is a different way from a different review of ours to put the essentially charge qubit and modifications, flux qubit and modifications, phase qubits. And there are 3 basic modifications, which is like shunt capacitance on the flux qubit, or on the charge qubit, or the fluxonium. And then there are different sources of noise, and then you can suppress both of them, or more the charge, or more the flux, etc. So this is a table, an overview of different artificial atoms that different groups are exploring around the world. So this is a big, like a bird's view of the field. Again, very pedagogical views are available on our website. So now I'm going to focus on the ultra-strong coupling of cavity QED first, an overview of the basics, and then the recent results. So now we're moving more toward the past 10 to 15 or so years. Let's start with a brief history of optics. You want to see where optics is going, let's look at instead of a brief history of time, by Hawking would be a brief history of optics in, let's say, 1 minute. So afterwards, I'm going to do a brief overview of cavity and circuit QED, a few minutes, then a brief overview of the ultrasound coupling USC limit of cavity QED. So this is cavity QED or circuit QED. Sorry, it could be cavity first and then circuit later. And then USC means ultra strong coupling, because it's not enough to have it strong, but it can be pushed to even stronger. And then a brief overview of the theory, and then a brief summary of different experiments using superconducting qubits. Let's start with a brief history of optics here. Long time ago, people were studying phenomena of optics with very many photons using classical optics. Over time, they were studying few photons, quantum optics, and then one photon, quantum optics. So therefore, the evolution is very clear. Very many photons, few photons, one photon. Then the future of optics involves no photons. Then quantum optics, or could be called vacuum quantum optics. Now, in the classical physics, quantum optics is the vacuum is empty. In quantum mechanics, quantum field theory, the vacuum is not empty. There are fluctuations, which I'll describe in a moment. So this is the harmonic oscillator, A dagger A, equally spaced energy levels. This is two-level system, up and down, ground state, steady state. And this is the coupling between light and matter. The three energy scales, bare energy here of the light and atom here is assumed between a resonance. In reality, this omega qubit, omega cavity in general is different, but let's assume they are the same. The dipole interaction energy is h bar omega is the units of frequency, Rabi frequency, and the energy loss. Of course, there are always energy losses. So these are there's an interplay between this energy scale gives rise to different physical regimes. So you start first with a weak coupling, strong coupling, ultra strong, deep strong coupling. So the dipole interaction energy is very, very weak because the atom, essentially dipole coupling is charge times distance. I mean, the size of the system. The atom is small, the charge is small, the coupling is very, very weak. So therefore, Harosh and company were working for a long time to bring it here to this regime here. And then that's interesting results. And Harosh got the Nobel Prize for results obtained actually with Jean-Michel Raymond, Michel Brun, and many others. Also here, the Purcell effect here, and then here, Rabi oscillation. These are results from Harosh, Jean-Michel Raymond, and others. And then the more recent stuff of the past 15 or so years, which is virtual photons dressed in the ground state, ultrasound coupling, and then also deep strong coupling. You go even further. That came afterwards. We're going to focus mostly on the ones in the middle here. So here is the one by Harosh Raymond exploring the quantum. Reaper atoms, these are high dipole moment because the atoms are elongated. So the atoms are looking a bit like a football. They are trying to look a bit like an antenna. If you want to couple it on the field, you need to elongate it. You need a good mirror so that the light goes back and forth many, many, many times so they can interact with the atoms. And then in this case, you can obtain it with electron gas, collective enhancement, and then one-dimensional resonator, small volume, increase the coupling, large effective dipole, with capacity coupling. The atom is not moving, it's fixed. So therefore, you have here the cavity here, so the photon is going back and forth here many, many times to enhance the coupling. And you can see the Purcell effect, ultra-low threshold lasers, single photon sources, quantum Rabi oscillation. Second generation quantum technology started with this, but then people start pushing further when the coupling is of the order of the bare frequencies, or at least 10%. This is a new regime of light matter coupling in the past 15 or so years, but it's still attracting interest. And then you can do ultrasound coupling and deep strong. This involves higher order and non-perturbative effects, modified optoelectronics, modified quantum optics, quantum vacuum emission, virtual photon engineering, light matter decoupling. So there are new phenomena that people are studying theoretically in the past 15 years, experimentally is ramping up in the past few years. So there's a review on this published some time ago on ultrasound coupling between light and matter. That was right before COVID, 2019. And then on Nature Reviews Physics by a former postdoc of mine as professor in Sweden, a collaborator in Poland, a collaborator in Italy, two collaborators in Italy, and here. And then So the key points is that this ultrasound coupling can be achieved, for example, by coupling many dipoles with light. Standard approximations break down, like rotating wave approximations, allowing processes that do not conserve the number of excitations in the system. This leads to a ground state that contains virtual excitations. This is important. So this involves superconducting circuits, Landau polaritons, organic molecules, intersupply optomechanics. This is very, very general, involving many different communities. Over time, the coupling becomes stronger and stronger and stronger, and this is the plot ended there because we did a review then, but it keeps going on among different communities. It is here as a study on deterministic quantum linear optics with single atom virtual photon. It's a very long one. Kind of online pedagogical one, but you can find these all, okay, the review and some specific ones on our website. We have PDF files and links to archive for all our papers. So you can find all our papers are essentially open access there. Also, we proposed about a decade ago how one photon can simultaneously excite two or more atoms. This was verified experimentally last year in RIKEN and published there. So we have some papers here with experimentalists here. And the experimentalists are highlighted there in yellow, but then I'm going to be focusing on the ones inside the green box, the blue box, because there's not enough time. Essentially, I'll describe it in a moment here. Exactly, it's only the ones inside the box. Let us now introduce the properties of the light matter ground state. So you have this oscillator here. You can have the field can have n photons, 0, 1, 2, 3. So this characterizes how many photons in the cavity. The qubit can be ground state excited state. So that's the only two possibilities. And let's ignore this coupling because there are too many terms here. So that's to characterize the state is very simple. Count the number of photons in the system up or down, ground state excited state. Now let's turn this one here. What happens? Then there is hybridization. This is called the light matter dress states. This is called the James-Cummings model. So the counter-rotating terms are ignored. Now the states are hybridized here. The ground state is still 0 photons in the cavity and the atom in the ground state. You're increasing the coupling between them. There's a coupling, and then this doesn't matter, but other ones change. What time when you do this? You will do it like this, then there is a shift. This is the analog of the Lamb shift that got the Nobel Prize to Lamb years ago. So the ground state actually shifted because it gets dressed also. Essentially, all the states get renormalized with different number of bare excitations because the ground state is not empty. And then there are virtual photons. So the expected number for the ground state is non-zero. These are called virtual photons because they are dressing the ground state. Renormalized. So you need to do a normalization group and then quantum field theory to study this. And again, in the classical physics, the vacuum is empty. There's nothing. The quantum mechanics ground state has a 0-point energy. So there are fluctuations even in the vacuum. So the vacuum is empty on average, but with fluctuations that can be described as virtual particles that spontaneously appear and disappear in pairs. In quantum field theory, this is done by looking at this bubble diagram. So you look at the Feynman diagram, this is time and this direction. And then these virtual particles, they collapse here, they appear and disappear. So this was predicted in the 1970 by somebody called Moore. I think he was a graduate student at the time. And then looking at these bubbles, these virtual photon bubbles, and he put a mirror here, and it was a Gedanken experiment made theoretically. What happens when you essentially break the pair? So you're creating two photon pair, but these two photon pair are entangled. They are from the same source. So by doing this repeatedly, you can create many photons from the vacuum, but you need to move the mirror here very, very fast. The people have been trying to do this for 40 years, and they couldn't do it because you move an actual mirror, you don't go very, very fast. So I'll explain to you how we solve this problem. Then 1974-75, Hawkins said, well, instead of using a mirror, then the event horizon acts like a very fast moving mirror because it's breaking virtual pairs. So therefore, the photon inside the event horizon is sucked in, and the one outside goes out. This one's here, they are recombined. So therefore, the pairs of virtual particles are broken up, one being trapped in the black hole on an escape. If you put a detector here, I do not know if it came from here or it came from a nearby star. Typically, there's a nearby stars which are cannibalized. So therefore, I don't see this as a very practical way to test a Hawking radiation, at least not in the lab. So we thought about this for a while. And then, so here there are vacuum quantum effects. This is a Lamb shift 1947. This cannot be predicted using normal quantum mechanics. This requires quantum field theory. And this was a big boost to quantum field theory in the 1940s, 1950s. This gave rise to the Lamb shift, and also Tomonaga, who was actually years ago, and Schwinger and Feynman. But then in 1948, okay, these are physical fluctuations with no classical counterparts. On, if somebody could turn off the microphone because there is. Okay, here we go. So then there is the 1948, the Casimir force, the experiment, the most important experiment is done by Federico Capasso at Harvard, done the most systematic, accurate, I mean, really impressive experiments. But this was in the 1970s. This should be called the Moore effect, but Schwinger decided to call it the Casimir effect, where the vacuum fluctuations are here on average, but by moving this mirror very, very quickly, you can generate the photon pairs here. And then there's also 1974 Hawking radiation, 76 Moore effect. These are all vacuum quantum effects. We have a review on these, if you're interested, on more than a decade ago, looking at the general relativity aspect, the quantum field aspect. They see mostly from a quantum optics perspective. So it's all unified. I think it's the only article I've seen putting all of this together in a systematic and organized manner, because typically these phenomena are studied separately. So therefore,
sorry, sir. For interpreting you, can you explain Casimir effect once more?
Sorry, is this, the questions are at the end. Let me continue, okay? Hello?
Yes, you can continue, and at the end, we will take the question.
Exactly. Otherwise, you never get to the end. And then again, if you're really interested, there is a very pedagogical review that has been cited hundreds of times. It's available for free. So people who really care, they can find a pedagogical review, which we spent a long time trying to explain. It takes about 24 pages. It's like it's starting from the basics. So it's done very, very pedagogical. It's highly cited. So all of this explained there for the people who really care. So therefore, the basic idea is here you have a pump here. You get a signal and an idler. This is a nonlinear medium. So therefore, this is a principal parametric amplifier. But then you can modify this in ways to relate to the Ponder effect. You have two more squeeze states. You have the equivalence principle of Hawking radiation with exponential redshift, dynamic Casimir effect, and single mode cavity here. So there are ways to relate them, but this is complicated. And then this requires an entire talk by itself. And then this relation between different quantum amplification mechanisms. And now let's talk about virtual photons in ultra strongly coupled systems, or quantum optics without real photons. So essentially, if you have two resonators in the ground state and one photon, two atoms in the ground state and one photon in the resonator, you cannot excite two atoms simultaneously. You cannot do that because there is this. You need another photon, but then the system can briefly borrow a second photon from chance fluctuations in the vacuum within the cavity. At that point, you access this virtual state. That's why this is a dashed line. These are virtual transitions, and then you can get here. And then this can be proved analytically, perturbation theory, numerically, and then this we proved this like about a decade ago. And then when you look at you diagonalize the Hamiltonian, you see this crossing here, but they are not really crossing. They are like avoided level crossings, where the two atoms in the ground state can be excited by a single photon. There's a rabbit flop in between them. This is avoided level crossing, means they're interacting, they're coupled. And these the two split energies correspond to maximally entangled three particles. You can generate maximally entangled three-particle state layers also. This can be done with more atoms, but it's a simpler one. So you can start with the system here. You put a pulse here, this Gaussian pulse. Then the Gaussian pulse comes here, and then the system goes into 2 qubits excited, one photon in the cavity, and the 2 qubits in the ground state, 2 qubits excited, and then so on and so forth. You can quantify it with a mean photon number, atom mean excitation number, zero delay, two atom correlation function. This is with no damping, this with damping. This is done by exciting the system, and you go into 2 qubits excited, none of them excited, with one photon. This was studied by looking at the spectral properties of two superconducting artificial atoms coupled to resonator in the ultrasound Doppler regime by Tomonaga and company and Stasi. Did a theory experiment and then helped other people. The head of the group was Yoshihara and Tsai. It was done in RIKEN. That was published about a year ago. So therefore, the main idea is that experiments theoretically investigated how the superconducting circuit qubit is ultra-stocked into a common resonator, and how the system, how essentially, let me put this one here, how one photon can simultaneously excite two artificial atoms by absorbing one photon from the resonator, and then okay, these are the 2 qubits, the green one and the blue one. There is here a resonator here which is very long, and then the photon is coming in, and then the resonator allows this essentially this coupling between them. So therefore, this is the optical microscopic image of the measured sample as a coil to bias uniform magnetic field in the back. Okay, exactly. This one you can control it. There's an on-chip bias. This one here, not the green one. So you measure this vector analyzer for probing and transition lines. So you put the photon here and see how it's affected by this system. There's a green qubit, the red qubit is about a few microns, as you can see there. Because many presentations are mostly theory, I would like you to see experiments, because the theory can relate to experiments here. So these qubits are almost identical, but then they can be proved to be in the ultra-strong coupling regime, because the coupling strength is more than 10%. There's something like that. So instead of being like 0.1, it's like 0.6 to 0.7. So it's definitely a strong coupling regime. The schematic diagram is the green qubit is coupled to the red qubit via this resonator here, this LC circuit. So these crosses are just on junctions. So this one here is talking to this one here via this coupler. This is like the data bus. This is an equivalent circuit diagram for the sample. So here you have the following. You have the spectral properties of two superconducting artificial atoms coupled to resonator in the ultra-strong coupling regime. These are the transition lines between, let's say, level 1 to 5, level 0 to 5, level 1 to 4, level 0 to 4, 3 to 1. So there are many transitions when you change the epsilon 1, the energy of qubit number 1. So this is the raw data, but when you do the calculation, you can see that the raw data can be matched very well with the theory. So there is a very nice correspondence between the data here and the theory. So here it is. So the pump frequency here on the vertical axis from this is the photons which are being pumped in. Whereas the persistent current energy of qubit 1. The qubit 1 is tuned via this flux qubit. So this is the raw data of the observed single-tone spectrum of the sample shown in figure 1. And then, exactly in this case, the fitted curves correspond to state transition frequencies omega ij between the ith atom and the j eigenstates of the Hamiltonian. And this is essentially the strength here. So now, if we enlarge this part here, the red dash rectangle here, you enlarge it here, then you can get this one here. So you're focusing the transition between levels 0, 3, 0, 4, 1, 5. And then you enlarge it again. So this is the enlarged view of the central part of the spectrum we saw before with the fitting curves. The fitting represents the spectrum very well. And then you enlarge this part here, you get this thing here. This is the pump frequency. This is the photon you're pumping in, and you're tuning one of the resonators, essentially like a trombone, like a resonator where you can actually, like a guitar string, where you can actually slide in the finger to change the length of the resonator here. And then or the coupling to resonator. In this case, you can see that there is an avoided level crossing between the system, which is ground state, one photon in the cavity, and excited atom, 0 photons in the cavity. And this is the essentially, so these are avoided level crossing. So the expectation value when you change epsilon 1 is that when epsilon 1 is small, you are in what is essentially one kind of transition is very highly probable, and other ones are more probable at other frequencies. So in this case, there's Rabi flopping between these two here. Okay, the large view here. So therefore, in this case, provides evidence of this exotic interaction that allows the simultaneous excitation of two artificial atoms by absorbing one photon from the resonator. Now, current experiments now are probing these on the time domain, but these ones are not completed yet. So this multi-atom ultra-strongly coupled system opens the door to study novel processes for quantum optics and quantum information tasks on a chip. This can be studied theoretically in this way. There are many, but this one here puts many of them together, which is how to do quantum linear optics in a deterministic way to see single atoms and virtual photons. So again, in linear optics, you require interaction between signals, exact information. That's why telephone companies, all these telecommunication companies interested in fiber optics, they have people studying nonlinearity in fiber optics because they need light to interact in this fiber optics for down conversion, up conversion. These interactions can be enabled by nonlinear optical processes, but these ones are weak. This includes optical modulation, optical switches, nonlinear spectroscopy, frequency conversion. They have applications on physical sciences, biological sciences, and engineering, like telecommunications. So you need to be able to achieve, so the goal is to be able to achieve optical modulation, optical switching, nonlinear spectroscopy. So this is something which is not quantum computing, but this is very, very important. There are many, many industries which are actually doing important work, essentially, like telecommunications. The problem is these nonlinear effects in optics are weak and require many photons. This is a big, big problem. This is to do general three-way mixing, where you put omega 1, omega 2, you get the sum, or down conversion, where you get one frequency, you get this, and the difference, because the energy is conserved here, mostly the sun dissipation is mostly conserved, or up conversion, down conversion, I call it this is continuous random scattering.
Professor Nori?
Yeah.
Can you please summarize in 5 minutes?
Summarize what?
Finish your talk in 5 minutes.
Oh, okay. I'll finish quickly. So here it is. So with this is strong coupling with a single photon and two photon states here. So this is the experiment done by Chen Chenyo and Tie-Fu Lee and others there. So here it is. So we have a signal here. So what you see here is a coupling waveguide resonator there. And then the flux qubit, the red one here is red, inside works as a nonlinear coupler between two modes of resonator, which is this one here, lambda over 2 and lambda. So therefore, there's a vacuum current distributions inside the system here. You want to couple the lowest mode of the organ pipe with the next mode of the organ pipe or the guitar string. So imagine this to be a guitar string at the quantum level or an organ pipe at the quantum level. You're looking at the two lowest modes, and you want to couple them. And you do with these three junctions here. You have this flux qubit inside. They're very nonlinear. And then you can do the loss rate is here, and the loss rate is there. And then setup is from here. This is how it looks like. It's about the order of 10 microns or so. This is the optical image of the flux qubit. And then you're trying to couple this with this. You cannot do it directly. You need to do it indirectly. And then how you do that? And then you first look at the energy level is complicated, but you look at here. There are a number of photons in the first two modes. This is the big mode at the bottom, ground state, excited state, and the ground state, and the atom is in the ground state. Then here, the qubit state. So you got 1 photon in the first mode resonator, and then 0 in the second one, 2 photons in the first mode, 0 in the second one, and the outer remains the ground state. But this, you cannot get these 2 photons here to go here directly. You need to go via virtual transitions involving 0 photon in the first 2 modes and the excited atom, or 1 photon in each mode and the resonator, and you can do it indirectly. And then you can actually split in the split here and the splitting. This can be proven that there is some Rabi flopping among these 2 states here, and this can be done. Essentially, this can be proved here, but it's okay. There's all kinds of theory to prove this here. Exactly, this Rabi flopping between these 2 states here can be done analytically, perturbation, numerically. You can see this on our paper. These are all these experiments here, and then you can see the effect is here. So let me see this one here. There's a Rabi flopping. So there is here a whatever crossing between the 0, 1 and 2, 0, essentially. So you can do here nonlinear optics, single harmonic generation with very few photons. This can be proved rigorously. And then so it's a near deterministic photon up-down conversion has been achieved before, but in our case we did it with pure photon up-down conversion without any atomic transitions. And then there are other things that can be proven there, but there is essentially the theory experiments match very well. And then we did experimental unstimulated strong coupling between a single photon and 4 photon pair. And then the other results here. And then there are some results here about the tau-less pumping. And then I'll show this one here. The tau-less pumping is the following. Essentially, is the quantum analog of the Panama Canal. Essentially, you do the on-site Coulomb potential goes up and down, the kinetic energy goes up and down, oscillating. And then when you do that, this one it oscillates here, you can get the wave function split forward. And then you can actually control the motion of the system. Essentially, is a quantum version of the Archimedes screw. So you do slowly pumping, and then you can do this, the quantum regime, and this is all on a chip here. And you can do like this, you can move things here to the left and to the right. You can actually control how the system is moving by changing the pump. And then at the end, there's a conclusion here. We are able to do tau-less pumping in a system here. And then this ends the talk. Thank you very much.
Thank you for the nice talk. Now we have time for a couple of questions. Sure.
One question. So thank you for a very interesting and informative talk. So my question is, you have discussed qubits in superconducting artificial atoms. So what about the prospects of generating and manipulating qubits?
Well, this is a very good question. There are several groups working on this, and I think the future, is promising this, at least at the level of basic science and experiment, because then open new possibilities. We have done theory, and we are collaborating with experimentalists on qubits. Namely, instead of having up and down 2 levels, like 3 levels, 4 levels, 5 levels, these are exciting also for memory storage, for communications, for encoding information in more than just 2 states. And there are exciting experiments on this, and then we have papers on this, and this is a very, very exciting area of research, but I couldn't cover it today, but it's a very good point.
Thank you.
I have a couple of questions.
Yeah.
One
Yeah,
is,
you go ahead.
if I understand properly, so what you are doing is you are taking a fixed resonator and you are sweeping the qubit frequency, and because of that, their eigenstate are crossing. So I wonder if you fix the qubit frequency and use a tunable resonator to address this problem, or is it going to make another problem? And my second question is, you talked about this giant atom that the sound is interacting with this qubit. So this superconducting qubit is QED, but the sound is mechanical wave. How you introduce that notion to this circuit QED? Thank you.
Okay, because the first question, yes, you can tune in principle the resonator or the qubit. It's simpler to tune the qubit, so that's a matter of simplicity, but both can be done. We have a theory and experiment where the resonators are tuned like a trombone, that can be done. But this gives simplicity. Question number 2, yes, the mechanical resonators, they couple to the substrate. The substrate is gallium arsenide that can have surface acoustic waves, and then the electrical signal is piezoelectric. It propagates, and it actually can excite the atom. This has been done on both ways. The capacitor exciting the qubit, or the qubit sending signal to the capacitor. So both can be done. And then, okay, so any other question, or that's the end of the session now?
Yeah, I have a question.
Go ahead.
You mentioned about a single photon being absorbed by two atoms. What is the role of entanglement there?
Can you repeat the question? Because it went a bit,
A single photon being absorbed by two atoms.
Yeah.
Is there any role entanglement plays there?
Yes, yes. Let me see this one here. In this case, yes, because as you can see here, this transition between GG2 and then it decouples into these states here. GE, these are not factorizable. These are not separable. And then
Okay.
here. So, but this is one of the intermediate states. And in general, if you do this for more, essentially, the two split eigenstates at the minimum splitting correspond to maximally entangled three-particle state. This is proved in our TRL. This is a TRL on this, and also a longer version afterwards. So this at the splitting is a maximally entangled three-particle state.
Okay, thank you. Yeah.
You're welcome.